It is my pleasure to introduce our next speaker to you. It is Dr. Debra Perrone. She is an assistant professor in environmental studies here at UCSB. Professor Perrone received her PhD in environmental engineering from Vanderbilt University and did a postdoc at Stanford University as part of the Civil and Environmental Engineering Department and Woods Institute. Professor Perrone studies water scarcity challenges and integrates methods across disciplines. And she uses these methods to inform water sustainability and policy. She has published widely and received multiple fellowships for her work. Professor Perrone today is here to talk to us about groundwater depletion and how it amplifies the water energy nexus. Please join me in welcoming Dr. Debra Perrone.
Thank you so much. Thank you for the invitation to speak today. So the work that I'm going to be presenting today is in collaboration with a number of colleagues, Scott Giuseco, Derek Wynn, Grant Ferguson, and Jennifer McIntosh. Today I'm going to share the story of an overlooked resource, how we can leverage hidden data to promote our understanding of this resource, and how overuse amplifies the water energy nexus. Today, I'm going to be talking about groundwater. Groundwater is often considered an invisible resource, and that's because it's hidden beneath our feet. While groundwater may be stored under our feet, when it comes to the surface, it provides more than half of our global population with drinking water. And it also provides more than 40% of the water used for irrigated agriculture globally. This map here shows irrigated area serviced by groundwater in a percent. And the black areas indicate 75 to 100%. So a good portion of the land area is irrigated by groundwater. And there's a number of areas that really stick out here. So we have China, we have India, the Middle East, and of course, the United States. And that's where I'm going to focus on today. So there's no doubt that groundwater is an important resource, but there's also no doubt that we are overusing groundwater in some places throughout the United States, which is leading to depletion. There are many undesirable results linked to groundwater depletion, such as land subsidence and saltwater intrusion. But there's one manifestation of groundwater depletion that has received little attention beyond the media, and that's when groundwater wells run dry. So when do groundwater wells run dry? Groundwater wells run dry when groundwater levels decline so significantly that pumps can no longer bring water to the surface. But until recently, it was hard to know where groundwater wells were vulnerable because well drilling is rarely studied. What does this mean in layperson terms? Well, this means that we didn't know where groundwater wells were constructed. We didn't know the purposes or the reasons for which they were constructed, and we didn't know the depths to which they were constructed. So we spent the past 5 years collecting, collating, and quality controlling data from each state and sometimes sub-state agency to put together an idea of where people are drilling groundwater wells. Why is this important? Well, groundwater wells are the very infrastructure used to bring groundwater from the subsurface to the surface so that we could use it for domestic uses, agricultural uses, and industrial uses. This map here shows 11.8 million groundwater wells, where each gray dot marks a groundwater well that was constructed between 1950 and 2015. If we categorize groundwater wells into 3 broad categories, we find that 83% of groundwater wells were constructed for domestic or municipal purposes, 15% for irrigated agriculture, and 2% for industry. Well reports also reveal the depths to which groundwater wells are constructed, providing a really important lens into the subsurface. Here, the light blue dots indicate shallower wells, and the dark blue indicates deeper wells. It's really important here to point out that before this map, we didn't have a really good idea about where people were drilling groundwater wells or the depths to which they were drilling groundwater wells. We got most of that information from local scale studies or anecdotal information from the media. This is the first time that we're really seeing trends across the United States stitched together. And we now know that the average groundwater well in the United States is 60 meters deep and the median is 44 meters. So we can use this information about groundwater well location and depth to get an idea about where groundwater wells ran dry during the peak of the most recent drought in the west of the United States. And what we found is that 1 in 30 groundwater wells ran dry, and in some areas, as many as 1 in 5 groundwater wells ran dry during the drought. So the question here is, what can we do when wells run dry? Well, one opportunity is to drill a deeper well. And so we asked the question, are people drilling deeper wells over time? Now, if you're from California or you have followed the news in California, well, you probably are thinking, well, yes, obviously, this is what the media is portraying. But we found some really interesting nuances, and I'm going to go through that today. So in addition to the information about the location, the reason for drilling, the depth of groundwater wells, groundwater well reports provide temporal information about when groundwater wells were constructed, so we can get a time series plot of depth trends. Let's use an example near Stockton, California. Across the x-axis, we have time. Across the y-axis, we have depth in meters below the land surface. And each one of these dots indicates a groundwater construction event. So this groundwater well in particular was constructed in the year 2000 at a depth of 100 meters. So we can do this same analysis across the United States, where each of these areas are indicating an area that has at least 100 groundwater wells constructed between the years 2000 and 2015. The blue here shows that groundwater wells are being drilled shallower over time, and the red that groundwater wells are being drilled deeper over time. And so even with a quick glance at this map, what we see is that there's more orange and red than blue, indicating that more times than others, we are drilling deeper groundwater wells. So across a wide range of scenarios, we find that groundwater well deepening is 1.4 to 10 times more common than well shallowing. But what's really unique about these groundwater well data is that we're able to see continental scale hotspots at local scales. So the map on the left here shows key aquifers where yellow and red indicates groundwater depletion since the early 1900s. The map on the right shows our groundwater well data. And the really important point here is that we can use this local scale water data to inform continental scale water challenges like groundwater depletion. To do this, we compare drilling depth trends with water level trends, and this can help us understand the relationship between declining water levels and deeper wells. On the right-hand side here, you see a satellite image. The blue dot in the middle indicates a monitoring well. The yellow dots surrounding that are constructed groundwater wells during the same period of interest. And these groundwater wells are within a 5-kilometer buffer. We want to explore trends here in an area that's sort of big enough that we can capture a statistical sample, but small enough that we could take into account some of the heterogeneity in the subsurface. So let's go back to our example near Stockton, California. The blue area shows water level time series, and what we see is over the period of interest, groundwater levels are declining at a rate of 3 meters per decade. Each of these yellow dots indicates a constructed groundwater well within that 5-kilometer buffer. And what we see is that over the period of interest, groundwater wells are being constructed deeper at a rate of 7 meters per decade. We can translate this information to a plot that can help us understand trends at a regional level. So across the x-axis, we have well completion depth. Anything that plots on the left side indicates a shallowing trend. Anything that plots on the right side indicates a deepening trend. Across the y-axis, we have the water level trend. Anything that plots across the top indicates a rising water level. Anything that plots across the bottom indicates a declining water level. And so for Stockton, California, what we know is that the wells are getting deeper over time, so we would expect to be in that right-hand quadrant. And the water levels are declining, so we would expect to be across the bottom 2 quadrants. And sure enough, for Stockton, California, we end up in that overlapping quadrant in the lower right-hand corner. So now if we zoom out, we can perform these same analyses for the entire Northern Central Valley, also known as the Sacramento Valley. On the left-hand side here, I show an example of what a zoomed out satellite image would look like, where the blue dots show the monitoring wells and the yellow circles in this case show those corresponding buffers. So in this region, the Northern Central Valley or the Sacramento Valley, we see that 83% of sites fall in that bottom right-hand corner, where a site is a monitoring well with water levels reported between 2000 and 2015, and nearby groundwater wells constructed during that same period. Performing this analysis for the San Joaquin and Tulare Lake regions of the Central Valley, we find very similar trends. Our work in this region suggests that for the most part, drilling deeper is not necessarily limited by the physical system, but instead by socioeconomics. We found that groundwater wells are expensive. Domestic wells can be tens of thousands of dollars, agricultural wells can cost hundreds of thousands of dollars, and municipal groundwater wells can be more than $1 million. People don't have the money to drill the new wells, and that's the biggest problem. This is a quote from Jim Smith, who lost his well to declining water levels during California's 2010s drought. So these findings, declining water levels and deeper drilling, have a number of implications on the water energy nexus. First, energy requirements increase with every foot water is lifted. So if we have declining water levels, that's going to require more energy to lift the water to the surface. Second, deeper water levels tend to occur in deeper wells. So as we construct deeper wells, we'll need more energy to lift the water. While pumping is typically a small percentage of a state's energy portfolio, especially outside places like the Central Valley, where solar is not as widely adopted, for individual farms, it can be a large portion of their energy portfolio. So the trends in California are distinct from trends that we see in many other places in the United States. If we move eastward to the High Plains Aquifer, another really important aquifer in the United States, especially for agriculture, the first thing that pops out here is that we have less clustering in that lower right-hand quadrant like we saw throughout the Central Valley. Here I'll point out that the different colors denote the different states. And this is really important because different states have different data collection policies. And so there's different biases that we're seeing in these big data. Now, while the northern and central high plains have really interesting trends, I want to draw your eyes to the southern high plains. Here we see that the dots are mostly spread across the bottom two quadrants, indicating declining groundwater levels, but also indicating that declining water levels are not always met by deeper drilling. In the southern high plains, we see that although monitoring wells indicate declining water levels, well depth trends are both shallowing and deepening. Upon a closer view of well logs and local groundwater management documents in the New Mexico portion of the high plains, we find that our results are complemented with concerns about the future of water availability. Here, deep groundwater is brackish to saline, requiring treatment before most uses, therefore increasing energy requirements. Additionally, deeper groundwater is not likely to provide the yields that make it worthwhile, so managers are looking to import alternative resources, which require additional energy for the conveyance of those water resources. Brackish water at depth is not unique to eastern New Mexico. In a recent paper, we found that several basins have less fresh groundwater than previously thought. We found that this fresh to brackish transition zone actually occurs at relatively shallow depths of just a few hundred meters in some areas. And you can see that in the red that's mapped here. We also found where in some places where we have fresh water at depth, these resources may be threatened by this pore space competition from the oil and gas industry. So the big question is, are deeper wells a solution or a stopgap to groundwater depletion? And here we suggest that that drilling deeper groundwater wells is actually a stopgap or a short-term solution that amplifies the water energy nexus for 4 key reasons. The first, energy requirements. The combination of declining water levels and deeper wells are increasing the energy intensity of pumping. Second, low permeability rock formations. At some point, groundwater users hit a bottom because of the hydrogeology. We saw this in eastern New Mexico. In places where groundwater aquifers have lower yields, communities may consider importing alternative sources, which requires additional energy. The third reason, brackish water with depth, we know that groundwater tends to get saltier with depth, so it may not be feasible to use water without desalination, which requires energy. And fourth, groundwater wells and groundwater pumping are expensive. As groundwater levels decline and folks need new wells, the cost may be prohibitive for some groundwater users. And so I'll close it up here and just highlight that these 4 regions not only highlight that there are challenges for groundwater depletion, but they also provide inspiration to move us towards groundwater sustainability. Thank you.